Could this discovery The observations reveal traces of simple minerals beginning to harden, marking the first steps in the birth of planets. And this is the part most people miss. These solids are forming within just 2.2 astronomical units of the star, a region akin to our own inner solar system, where temperatures are just right for condensation to occur. Why is HOPS 315 such a big deal? While astronomers frequently observe planet-forming disks, they usually catch them after large planets have already carved out gaps. This time, however, we're seeing the very start line, the moment when rocky building blocks Here's the bold part. The minerals detected around HOPS 315 appear in a region strikingly similar to where we find asteroids in our own solar system. This suggests that the early steps of planet formation might be universal across young star systems. But does this mean all rocky planets follow the same blueprint? That's a question worth debating. The telescopes revealed fascinating details. Webb's infrared spectra detected warm silicon monoxide gas and silicate crystals near the star, while ALMA pinpointed their location in the inner disk, separating them from confusing outflow and jet activity. According to Melissa McClure, lead author of the study, this is the earliest moment of planet formation ever identified around a star other than our sun. So how does this all happen? Near a young star, temperatures are high enough to vaporize rock. As things cool, the toughest materials, like silicon monoxide, begin to solidify into tiny crystals. These grains collide, stick together, and grow into planetesimals, eventually becoming rocky planets under the influence of gravity. The exact composition of these early condensates depends on temperature, pressure, and the movement of material within the disk. Observations like these tell us which minerals appear first and where, shaping the chemistry of future rocky cores and atmospheres. Ancient meteorites in our solar system offer clues to this process. Calcium aluminum-rich inclusions, CAIs, found in meteorites are among the oldest solids from the Sun's nebula, dating back to the very beginning of our solar system. These inclusions, along with later melt droplets called chondrules, provide a timeline of planet formation. The new detection around HOPS 315 gives us a direct view of a similar process in action around another star, strengthening our understanding of how planets come to be. Looking ahead, HOPS 315 offers astronomers a pristine target to study how quickly solids grow in the inner disk. Repeated observations could track changes in the gas-to-solid ratio and reveal the pace of grain growth from dust to pebbles to rocks. Future data might also answer whether this process is common across the galaxy or a rare occurrence. The immediate goal? Expand the search to more young stars. If multiple systems show the same early signatures, the first steps toward rocky planets might be more routine than we thought. This discovery not only opens the door to timing the earliest phases of planet assembly, but also sets a benchmark for models aiming to explain how Earth-like planets emerge. But here's the thought-provoking question. If these early stages are indeed universal, what does that imply about the likelihood of finding other Earth-like planets out there? Share your thoughts in the comments. We'd love to hear your take. If you're as fascinated by this as we are, subscribe to our newsletter for more engaging articles and the latest updates. And don't forget to check out EarthSnap, our free app brought to you by Eric Rolls and Earth.com for more incredible insights into our universe.